Hi everyone, this is Mrs. G.A. and today we're going to be finding volumes using cross sections. Alright, I have a warm-up for you guys. We're going to be using some of these today, so please pause the video and fill out the chart as much as you can. Alright, go ahead and check your work here. So sometimes we need to kind of redefine different parts of our shape in terms of B, but here you can see are all the areas in terms of B. So the reason why we did this for the warm-up is because today we're going to be forming volumes using cross sections. So sometimes those cross sections might be squares, sometimes they might be semicircles, sometimes they might be trapezoids. So it's important to be able to find the area of those different shapes, regardless of which part is actually the base, because sometimes the long side will be the base, sometimes your hypotenuse will be the base of your three-dimensional solid. So being able to define the area in terms of different sides is going to be very important. So again, today we're going to be finding area of volumes that are created by cross sections. So previously we were working with volumes that were generated by rotating a bounded region around an axis or a line, but you can also form a three-dimensional solid by taking a base region. So that base region is defined by your functions, and then having cross-sectional areas rising out of that base. So there's no rotation for these problems. So here, if you look at this volume, the original shape, or the base, is formed by this equation, x equals 4 minus y squared, and it's, bounded by our y-axis. So this is the base of our three-dimensional shape. And then from there, if you draw a square, this one happens to have a square cross-section coming up out of that base, and then you kind of slide it over the length of your base, you can create this volume, or this solid. So this is what we're going to be finding the volume of today. Here's another example of a solid that has this looks to be equilateral triangle cross section. So again, here you can see, here it's a little bit difficult to see. I'll draw it in red. This is the base of our solid, which is formed by a bounded area with this quadratic equation. And then you can see out of that solid is coming these cross sections, which would be equilateral triangles, or it looks like they're equilateral triangles in this case. Then you kind of slide that along this way and it will form that solid. So when we are finding the volume of these types of solids, we still need to start by finding our bounded area, and then we need to find a way to describe the area of our cross section in terms of the functions we're working with. And then we will integrate over the integral a to b. So here you can see that we're sliding our cross sections along the x-axis. So here we'd be integrating with respect to x. Same for this one, we're kind of sliding it along the x-axis, but sometimes we'll be sliding our cross-sections along the y-axis, in which case we would be differentiating with respect to y. So for these, you do just need to be very careful about how you set up your integral and how you set your limits of integration. All right, let's give one of these a try together. So here we want the volume of a solid whose base is bounded by this circle, x squared plus y squared equals 1. So we can sketch that really quick. That's just a circle with the center at the origin, and the radius is equal to 1. So it looks like this. Again, we're just saying here is 1, here is negative 1, 1, negative 1. And it says that each cross-section perpendicular to the x-axis is a square. So that means that our cross sections would look like this. They're perpendicular to the x-axis, and each cross section is a square. So this would actually just be one side of our square, just to kind of help you visualize a little bit more. I know you kind of use this like flattened out axis. So here's our circle, and here's our y-axis and our x-axis. So this is the same line that I drew right here. So the cross section is a square, so it would look something like this. And then this is our cross section, and then you can see that we're going to be sliding that along the x-axis. So we're going to be integrating with respect to x. So again, this distance here is the same as this distance here. So this is just one side of our square. So this is on one side. We know that for the area of a square, the length and the width are the same, so it's just going to be whatever this distance is squared. So again, our volume is going to be the integral of the area of our square. And this one, since we are sliding, again, horizontally along the x-axis like this, we're integrating with respect to x. So now we just need to find a way to define the area of the square in terms of our equation. So we need to find a way to determine this length. So we do always want to do top minus bottom. So if we want top minus bottom and we want this vertical distance, we need to rewrite our equation in terms of y. So I can rewrite this as y squared equals 1 minus x squared. So y equals plus or minus square root of 1 minus x squared. So actually, the top half of our circle up here is going to be defined as the positive square root of 1 minus x squared. And the bottom half of our circle here is the negative square root of 1 minus x squared. So if I want to define the side length, again, the side of our square cross section, it's always going to be top minus bottom. And in this case, I'll say S for side, the top equation is represented by the positive square root of 1 minus x squared minus the negative square root of 1 minus x squared, which is just like saying square root of 1 minus x squared plus square root of 1 minus x squared. So our side length is just 2 times the square root of 1 minus x squared. So that's the side of our square, but we know the area of a square is just side squared, the integral of our s value squared dx. And now we're ready to set up our volume integral. So again, we're sliding this from left to right. So we're differentiating with respect to x, and we need to set our limits of integration with respect to x. So from -1 to 1, and it's the length of our side, all of this squared dx. So the first thing I would definitely do to evaluate this, I'm going to square my 2 and then pull it out front. And if I square the rest, I have 1 minus x squared dx. And maybe just to save some time, I can actually use symmetry here. I can see the right half of this volume is going to be the same as the left half. So I can actually just use the integral from 0 to 1 and then double it, so that 4 out front becomes an 8, and then it's just from 0 to 1. So the reason I chose to use symmetry in this one is because it can save us a little bit of time. When you're evaluating this by hand, it's much easier to work with a 0 than a -1, but you don't have to do it. It's just something that might, again, save you a little bit of time. So here we have x minus 1/3 x cubed evaluated just from 0 to 1. So we're essentially just plugging in 1. So when we plug in 0, it's just 0. So 8 times 1 minus 1/3 and then minus 0. So that gives us 16/3 units cubed. So there you go. So here, again, it's the first step is first kind of visualizing what type of solid we're working with, and then determining how to define the side of your cross section in terms of the equations you're working with. Then you have to see how you're sliding that cross section. So again, if you're sliding it or stacking them horizontally, you're going to differentiate with respect to x. If you were stacking them vertically, then you would differentiate with respect to y. So you have to be really careful with how those cross sections are defined. All right, let's try another one together. So here we have the volume of a solid whose base is bounded by x equals y squared and x equals 9. So let's start with that first. So we have a parabola that opens to the right, and then we know that when x is equal to 9, right here, that means that y is equal to 3. So this is at positive 3, this is at negative 3, and then this is at 9. Okay, so this is the base of our solid, and then it says that each cross-section perpendicular to the y-axis is a semicircle. So this time it's perpendicular to our y-axis, so it's going to be horizontal, and it says each cross-section is a semicircle, so it's going to look kind of something like this. And no matter where you draw it, again, your cross-section is going to be a semicircle. So we can see that this distance from here to here is the diameter of our semicircle. So we know we need to find a way to describe the area of this semicircle. So we know the area of the semicircle is going to be 1/2 pi r squared, and we need to find a way to define r. So first we can start by defining our diameter. So the diameter is going to be right minus left. And here we do want it to say x equals because it is a horizontal distance. So our diameter is, the rightmost function is just x equals 9. The left function is going to be y squared. So we know that if our diameter is 9 minus y squared, our radius is simply 9 minus y squared all over 2. So now we have a way to describe the area of each individual semicircle. So it's 1/2 pi times 9 minus y squared over 2, and then that radius squared. So now when we set up our integral, you'll see that we're stacking, or we're kind of sliding our semicircles vertically. So we're going from low to high, so we're integrating with respect to y. So we need our limits of integration to also be with respect to y. So it's going to be from negative 3 to 3 of 1/2 pi r squared dy. And then from here, it's just a matter of simplifying. So first I would pull out the 1/2 pi, and I would also pull out the 1/4 when you square your entire radius. So we can actually pull out 1/8 pi. And then let's make our work a little bit, well, I'll set up this first. And then we're going to actually use symmetry to help us out a little bit more. So pull out any constant first, and then we'll notice again that this is symmetrical. The top half of our volume is going to be equal to the bottom half of our volume, so we can actually just find half of it and double it. So we'll multiply this by 2 out front, so it becomes pi over 4, and then we just need to integrate from 0 to 3. And then for this, we would want to actually multiply out this binomial like this, dy, and then it's just evaluating our indefinite integral. So we have pi over 4, and then we have 81y minus 6y cubed plus 1/5 y to the 5th, evaluated from 0 to 3. So we're going to substitute in 3. And then if we substitute 0, everything goes to 0. And then from here, we're just simplifying our fractions. So we get 648 pi over 20, so 162 pi over 5. And then that is a volume, so it would be units cubed. So everything, from here on down is what we learned last chapter. It's just evaluating an indefinite integral. So the stuff to focus on for this lesson is to understand the setup of our integral, how we draw our picture, how we draw our cross-section, how we define the radius of this semicircle, and understanding, why we're integrating with respect to y in this case instead of with respect to x. So again, we're really focusing on these first 3 lines right here, and then the rest is really the stuff we learned last chapter. All right, I have one for you to try on your own, so please pause the video and give it a shot. All right, go ahead and check your work here. So here's our bounded area for our base, and it says that each cross-section perpendicular to the x-axis is a semicircle. So these semicircles are going to look like this at the base. They're perpendicular to the x-axis. So this would represent the diameter of our semicircle. Then it would kind of, like rotate around like that. And see that we're sliding our semicircles from left to right. So that's why we're integrating with respect to x. So if this is the diameter of our semicircle, we do top minus bottom, which is just square root of x minus 0. That means that the radius is half of that, so square root of x over 2. So the area of any individual semicircle would be 1/2 pi times root x over 2 squared, 1/2 pi r squared. And then we're just integrating this area with over the interval 0 to 9, because again, we're sliding from left to right. I pulled out the constant of 1/8 pi, and then I squared this to just get x dx, and then we can evaluate pretty quickly. All right, I have another one for you to try on your own. So again, please pause the video and give it a shot. All right, go ahead and check your work here. So here's our bounded region. And it says each cross section is perpendicular to the y-axis, and each cross section is a square. So this length would represent the side length of our square. And to define this distance, we need to do the right minus the left. Now, if we have this as our function, y equals x squared, we do need to define this as x equals. It's a horizontal distance, so I want to know what x is equal to. So the right half of our graph, we can define as x equals the positive square root of y, and this left half of our graph is x equals the negative square root of y. So when we do right minus left, we actually end up with 2 root y as our side length. And of course, to find the area of a square, it's just our side length squared. So 2 root y, all of that squared. So then here you can see that we're going to be sliding each cross section vertically, so from bottom to top. So we have to integrate with respect to y, so it's from 0 to 9. They're kind of stacking on top of each other. So here's the setup. Again, this is what we're really focused on today. And then I pulled out the constant and evaluated my integral. All right, let's try one more together. So this one, the type of cross section makes it a little bit trickier, but we'll work through it. So it says the base of our solid is a circle centered at the origin with a radius of 3. So it might actually help to define that equation. We're also going to graph it. So if it's centered at the origin with a radius of 3, here's the equation. So let's sketch that on our axis. Something like this. So 3, negative 3, 3, negative 3. Find the volume of the solid if the cross sections perpendicular to the x-axis are equilateral triangles. So first let's start by drawing a line that is perpendicular to the x-axis. So it looks like this. And those cross sections are all going to be, again, equilateral triangles. So if, you kind of want to visualize what's happening like this. Here's our x and our y. They're all going to look like this, something like this, and it's going to be slid horizontally across our x-axis. So this distance here to here, this represents the base. This is the base of the triangle, of our equilateral triangle. So I'm going to actually just draw an equilateral triangle down here. So first, let's find a way to define this base. We want to do top minus bottom. So to find our base, it's going to be top minus bottom. And kind of like we did in that previous example, we want to rewrite this as actually 2 separate equations. So the top half of our circle is the positive square root of 9 minus x squared. The bottom half of our circle can be defined as the negative square root of 9 minus x squared. And then we have to do, again, top minus bottom. So the base of our triangle is the top equation minus the bottom equation. So the base is 2 times the square root of 9 minus x squared. So that's this distance right here. But we know to find the area of this triangle, we need 1/2 times the base times the height. So we need to now find a way to describe this height. So if I drop an altitude right here, if we know this was an equilateral triangle, we know that this is 60 degrees and this is 30 degrees. So I'm going to even break this down even more to help us out. This kind of ties into the warm-up. So this distance right here is going to be this distance right here. So it's just half of our full base. So it's going to be square root of 9 minus x squared. And again, this is our 60 and this is our 30. And so we want to define the height right here. So we know for a 30, 60, 90, the ratio of the sides is 1 to root 3. So this leg is always going to be your shorter leg times root 3. So it's actually root 3 times the square root of 9 minus x squared. So that's going to be the height of our triangle. So the height is this square root of 3 times square root of 9 minus x squared. The base is this, and now we have a way of defining the area of each triangle. So 1/2 times the base times the height. So root 3 times the square root of 9 minus x squared. And again, this distance right here, or this value, represents our base, and all of this represents the height. Okay, so now the hard part is done. We can actually simplify that area just a little bit. The 1/2 and the 2 cancel out. These two radicals will just become 9 minus x squared. So we have root 3 times 9 minus x squared as the area of each individual triangle. And then we can see that, again, we're sliding this triangle from left to right. So we're sliding the triangles horizontally. So we're going to differentiate with, or integrate with respect to x. So from -3 to 3 of this area, root 3 times 9 minus x squared dx. So again, we can just pull out the root 3. And if we want, we can use symmetry to help us. So we can actually double that volume and then just go from 0 to 3, or from -3 to 0. But again, we know that this is going to be symmetrical over our x-axis, over our y-axis, so we can just do 0 to 3 and we can double it. You don't have to do that, but it might just make it a little bit easier. So 9 minus x squared dx, and now we're ready to evaluate. So that gives us 2 root 3 times 9x minus 1/3 x cubed from 0 to 3. So 27 minus 9. So 2 root 3 times 18, which gives us 36 root 3, and then units cubed. So again, for this one, I would definitely call it more of a challenge problem, but if you look at what the tricky stuff was, this is actually all geometry. So understanding how to define the different parts of your triangle in terms of your base, because we define our base in terms of our initial equation. So again, a little bit trickier, but it should definitely be doable, given a little extra time. All right, so that is all for today's video. Thank you so much for watching.